do a problem using C plus IS method. The question is, sum the series sine square theta minus half times sine 2 theta into sine square theta plus 1 by 3 times sine 3 theta sine cube theta minus 1 by 4 times sine 4 theta sine raised to 4 theta plus etc. infinity. Using C plus IS method, we name the given series as S and we find the corresponding cosine series by replacing sine terms sine theta, sine 2 theta, sine 3 theta by cos theta, cos 2 theta, cos 3 theta. We are making use of the cosine series C because we wish to apply cos theta plus I sine theta equals e raised to I theta, which is the popular Euler's identity. We have to replace only the linear powered sine terms sine theta, sine 2 theta, sine 3 theta using cos theta, cos 2 theta, cos 3 theta. In order that we have to apply the Euler's identity. We cannot apply Euler's identity to combinations sine square theta plus I times cos square theta, sine cube theta plus I times cos cube theta. For such combinations we cannot apply Euler's identity. That's why we are making use of replacement of only linear sine terms to corresponding cosine terms in order to frame the cosine series. This linear term sine theta is not changed because we have to take sine theta common outside from these two similar terms in order to replace cos theta plus I sine theta by e raised to I theta. So we frame the cosine series for each question looking at the behavior of the given series, given sine series. Now, since we have framed the C series, which is the cosine series, looking at the sine series given in question, we will now group terms which are of similar fashion and such that we can apply Euler's identity. When we group these two terms, we have sine theta taken common outside, cos theta plus I sine theta is the other factor, grouping first two terms. Similarly, when second terms half sine 2 theta into sine square theta and half cos 2 theta into sine square theta are grouped, we have minus sine square theta into 1 by 2 common taken outside and we are left out with cos 2 theta plus I sine 2 theta. Similarly, when we group the third terms of S series and C series, we have sine cube theta into 1 by 3 taken common outside and we have cos 3 theta plus I sine theta is the other factor when we group the third terms of S and C series respectively. So we can replace this bracket cos theta plus I sine theta by e raised to I theta. Cos 2 theta plus I sine 2 theta can be replaced by e raised to I 2 theta. Cos 3 theta plus I sine 3 theta can be replaced by e raised to I 3 theta. Notice that we are able to group terms in this manner after multiplying the sine series S with I and after that adding it with the C series. That's why the LHS is C plus IS. We get C plus IS by adding terms of C series to terms of S series after terms of S series have been multiplied by I. Applying Euler's identity to every term, we now have C plus IS of the format e raised to I theta sin theta minus e raised to 2I theta sin square theta by 2 plus e raised to 3I theta sin cube theta by 3 minus etc. We have log 1 plus x equals x minus x square by 2 plus x cube by 3 minus x raised to 4 by 4 plus etc. If we give x equals e raised to I theta sin theta, you can see that this series when replaced by x equals e raised to I theta sin theta has the similar or exactly the same series which is appearing in the RHS of C plus IS that we have evaluated. So, this RHS can now be replaced by the expression log of 1 plus e raised to I theta sin theta. We again apply e raised to I theta or the Euler's identity here in e raised to I theta, which is replaced by cos theta plus I sin theta. We have log of 1 plus cos theta sin theta plus I times sin square theta, which is obtained as the expression for C plus IS. Now we will have to separate real and imaginary parts. Then only we can find out the corresponding expression for S. We are looking for summation of the given series, and we have named the given series as S. So now we wish to separate the real and imaginary parts of logarithmic function, which we have obtained as the RHS of C plus IS. Recall the method of separation of log alpha plus I beta to real and imaginary parts. We assume alpha plus I beta equals R times cos theta plus I sin theta, from where we have alpha equals R cos theta and beta equals R sin theta. Number it as equations 1 and 2 respectively. When you square and add equations 1 and 2, you obtain R square equals alpha square plus beta square, which gives R equals square root of alpha square plus beta square. When you divide equation 2 by equation 1, we have R gets cancelled from the numerator and denominator. We are left out with tan theta equals beta by alpha, from where we have theta equals tan inverse beta by alpha. Now we can rewrite log alpha plus I beta as log of R times cos theta plus I sin theta, which can also be written as log of R e raised to I theta by using the same Euler's identity. We can write log of AB as log A plus log B. Also, log of A raised to B can be written as B log A. Using the two laws of logarithm, we can write log R e raised to I theta as log R plus I theta log E. Log E can be replaced by 1. Now we replace R by square root of alpha square plus beta square, which we already obtained from here, and theta can be replaced by tan inverse beta by alpha. This is of the form log alpha square plus beta square the whole raised to half. Since we have log A raised to B can be written as B log A, we have log alpha square plus beta square the whole raised to 1 by 2 can be written as half times log alpha square plus beta square. We have the imaginary part of log alpha plus I beta given as tan inverse beta by alpha. That is tan inverse of imaginary part of function appearing inside the logarithmic function, and the denominator alpha is the real part of function appearing inside the logarithmic function. Here we have log 1 plus cos theta sin theta plus I times sin square theta. So this much is the real part alpha, and this sin square theta is the imaginary part beta. Now we can easily equate real and imaginary parts. Here the imaginary part is S, which is the given series, and here the imaginary part is sin square theta, which is inside logarithmic function. Therefore, the corresponding imaginary part for the given logarithmic function will be tan inverse beta by alpha, where beta equals sin square theta and alpha equals 1 plus cos theta sin theta. Therefore, we have tan inverse beta by alpha for this function written as tan inverse sin square theta by 1 plus cos theta sin theta. Since we obtained S equals tan inverse sin square theta by 1 plus cos theta sin theta, the required sum of the given series is S itself.